Welcome back to the deep dive. Today we're getting into QwenLong L1.5 from Alibaba Group. We're going to be analyzing what is, I think, one of the most comprehensive post-training recipes we've seen this year for long context reasoning. Our mission here is to give you a really high-resolution technical overview of the paper. We're not just summarizing, we're trying to distill the core innovations, the results, and how they build a single system that can handle anything from, say, 32K tokens all the way up to a staggering 4 million.
And when you really unpack it, you see it's a full engineering effort built on three really interdependent pillars.
Okay.
First, you've got this systematic long-context data synthesis pipeline. It's designed specifically to create tasks that demand deep reasoning. Second, they develop stabilized reinforcement learning methods, which are just crucial for these super long sequences. And finally, a memory-augmented architecture. That's the piece that lets them tackle the ultra-long contexts, the 1M to 4M token range.
And the results really back it up. Their main model, the 30B version, hit an average score of 71.82. The paper puts it in the same league as models like GPT-5 and Gemini-2.5-Pro, and maybe most importantly, it beat its own baseline by almost 10 full points. So, okay, let's unpack this, starting with the data. The paper makes this really strong point that true long context reasoning means moving past simple, needle in a haystack tasks.
Right. They needed to force things like multi-hop grounding, where the evidence is scattered everywhere.
Which means you can't just find existing data, you have to build it.
You have to build it programmatically. Their synthesis pipeline is all about deconstructing source documents into atomic facts and relationships. That lets them compose these complex, verifiable questions from the ground up.
So how did they actually do that?
They used three specialized data engines. The first one is for what they call in-depth multi-hop reasoning. It's guided by a knowledge graph framework. So they extract triplets from documents, merge them into a big cross-document KG, and then use things like random walk and breadth-first search to generate these long-range reasoning paths.
So the traversal methods ensure the evidence is sparse and spread out.
Exactly. It's not all neatly packed in one paragraph. And to make it even harder, I saw you noted this, they use information perturbation.
Yeah, that caught my eye. They're obfuscating entities.
Deliberately, they might use a temporal description or an institutional name instead of the actual entity, forcing the model to synthesize clues from multiple places just to figure out what it's even talking about.
So no easy pattern matching.
No. The second engine tackles corpus-level numerical reasoning. This is all about precision.
Right.
They use a structural tabular data engine. It basically formalizes data from different sources into one big unified table and then translates natural language questions into executable SQL queries.
Ah, so the ground truth is guaranteed to be correct because it comes from a SQL query.
Precisely. And it forces the model to do things like statistical aggregation, temporal reasoning, tasks that need a global view.
Okay, so that covers structured reasoning. But what about more abstract tasks, like analyzing different viewpoints or long in-context learning?
For that, they used the multi-agent self-evolve framework, or MS. It's a team of 3 agents: a proposer, a solver, and a verifier.
And how does that increase difficulty?
The key is that the proposer agent is conditioned on a history of tasks that have already been solved. It's penalized for redundancy, so it's constantly forced to generate harder, more novel questions. It's a clever way to avoid generating trivial variations.
And once all this data is generated, they have to verify it.
2 critical checks. The knowledge grounding check filters out any sample where the model could just use its internal parametric knowledge.
It has to use the context.
Strictly. And the second is a contextual robustness check. They discard any sample where you can dump in a ton of irrelevant context, and the model's accuracy doesn't drop at all.
Because if noise doesn't hurt it, the task wasn't hard enough.
Exactly. It wasn't stressing the model's ability to discriminate.
That is a very robust pipeline. But having great data is one thing, actually training on it is another. Let's move to the RL methodology. What was the biggest hurdle they faced there?
Well, the fundamental constraint is just the quadratic complexity of attention. For long contexts, standard RL methods like PPO are just. They're computationally infeasible.
Because of the value network. It needs to run full self-attention over that huge sequence.
You can't do it. So their baseline is GRPO, Group Relative Policy Optimization. It's clever because it gets rid of the value network entirely. It estimates the advantage, the AI, using a group-wise z-score normalization of the rewards from the policy rollouts themselves.
So it's purely on policy.
Strictly on policy, and they found that setting the KL regularization beta to 0 worked best. It's an engineering necessity once you pass, say, 64K tokens.
But even with GRPO, they still hit stability problems with this new data.
They did. The issue was the multi-clustered nature of the data. You have all these different task types, and their reward distributions are completely different. This leads to severe distributional drift and reward bias in the mini batches. It makes training very volatile.
So how did they stabilize that dynamic without going to a more complex off-policy method?
Two really targeted modifications. The first is task balance sampling. Instead of random sampling, they made sure every mini batch had an equal number of samples from 5 designated task types.
Wait, doesn't that distort the training distribution?
Yeah.
I mean, if the real world is imbalanced, aren't you training the model on an artificial reality?
That's a great question, and I think they address it implicitly with the second technique, which is more important. It's task-specific advantage estimation.
Okay.
So instead of normalizing the advantage, using the standard deviation of rewards from the whole batch, they only use the standard deviation of rewards from samples of the same task within that batch.
Ah, so you're isolating the reward scales.
You're isolating them completely. A dense reward task can't bias the advantage estimate for a sparse reward task anymore. It stops a huge gradient from one sample type from destabilizing the updates for another.
That makes sense.
Sure.
But this is where I think it gets really interesting when they dig into the credit assignment problem that's so unique to long context reasoning. Table 3 shows the RJL overlap between a right answer and a wrong answer can be incredibly high.
Yeah, around 45% for some tasks. And that is a nightmare for RL. It means an incorrect reasoning path might be 90% correct, but just fail on the final crucial step.
The reward signal must be incredibly noisy.
Extremely. It's almost impossible to assign credit or blame accurately, especially for the negative rollouts, the wrong answers.
Which is what led them to the AEPO algorithm.
Exactly. Adaptive entropy-controlled policy optimization. The motivation was this empirical finding. They saw that high entropy tokens were strongly correlated with high gradient norms in those negative rollouts. The Spearman correlation was 0.96.
So high entropy, meaning the model's exploring wildly, is also where these destructive gradients are coming from.
That's the connection. So AEPO dynamically controls this. It sets up a control loop based on the batch entropy H.
So it's watching how chaotic the model is.
Right. If the entropy H goes above some high threshold, high, it means things are too chaotic. So, in that state, it masks all the negative samples. It forces pure exploitation, which brings the entropy back down.
And if it gets too low?
If H drops below how, it means the policy is getting too conservative, too stuck. So it reintroduces the negative gradients to encourage necessary exploration. It only penalizes that runaway exploration when the model is already unstable. That dynamic control alone gave them a 3.29-point gain.
That whole stabilization stack seems to be the key for whole context reasoning. But let's shift to the next level, ultra-long context. Even with these RL tricks, you're not getting to 4 million tokens with full attention.
No, you hit a hard physical limit. So to go beyond their model's 128K window, they introduced the memory agent framework.
And this reframes the problem entirely.
It does. It sees reading comprehension not as a single pass, but as a sequential decision-making process. The long document is broken into chunks.
Okay.
At each step, the policy updates its memory, MT, and this is the critical part. It generates a navigational plan, PT, for what to do with the next chunk. It's learning how to read.
So the agent is actively planning its path through the document, updating its own knowledge, deciding what's relevant next.
Precisely. The final answer is only generated after K steps using the final accumulated memory, MK, and the original instructions. It lets the model fold a massive context into a compact representation.
So how do you integrate this agentic ability with the full context model you've already trained?
Very carefully, it turns out. They used progressive training paradigm. They did a multi-stage length extension. Stage 1 at 32K, Stage 2 at 60K, Stage 3 at 120K, and they extended the max output length at the same time up to 50K tokens so the model could generate long answers.
So why not just mix the memory agent training data in with that Stage 3 data?
They tried, and they found it just wrecked the stability. It led to mode collapse, so they had to specialize. The memory management RL training was done after Stage 3, creating a dedicated expert model for memory and planning.
And then they fused them.
They fused them. They used an algorithm called SCE to merge the specialized memory model back with the full context model, and then did one final full context RL stage to unify everything into a single cohesive model.
Okay, so let's get to the payoff.
Yeah.
What does this whole systematic effort mean for performance? Let's look at the results.
The results are strong. The average score of 71.82 across the board is impressive, but the interesting part is where the biggest gains came from. On MRCR, they saw plus 31.72 point gain. On Corpus QA, plus 9.69.
And those are the benchmarks with the longest average context lengths.
Exactly. 36.5K and 92.8K tokens, respectively. It's a direct validation of the progressive length strategy. And on Corpus QA, which requires a ton of aggregation and calculation, their score of 81.25 is right there with the reported GPT-5 score of 81.56.
And what about the memory agent? How did it do on those extreme scales, 512K and up, where full attention is impossible?
It demonstrated real robustness. On a 4 million token subset of Corpus QA, the memory agent scored 14.29. That proves it can extract and synthesize information from these massive documents.
That's a non-zero score on a task that's just intractable for other methods.
Right. And on the 512K to 1M token subset of MRCR, it beat the baseline agent configuration by over 18 points. That's a huge margin, and it confirms that the learned memory compression and navigational planning are really effective.
So beyond these specific long context tasks, did the skills generalize? This is always the big question. Did they get catastrophic forgetting on other reasoning tasks?
No, quite the opposite. They avoided it completely. The skills actually transferred positively. The model's enhanced ability to integrate information led to gains on tough reasoning tasks like AEPO and GPQA Diamond. It's not just retrieving better, it's genuinely reasoning better. And the benefits were even more pronounced on memory-centric agentic tasks. A huge 15.6-point gain on long-meval for dialogue memory, and a nearly 6-point gain on memory KV, which tests handling of structured agent history. So these gains across different domains really confirm that pushing information integration gives a foundational boost to the model's overall cognitive toolkit.
So that really brings us to the end of this deep dive. QwenLong L1.5 seems to have successfully unified its single-pass reasoning up to 128K with its iterative memory agent scaling beyond 1 million tokens, all in one model.
It's a very comprehensive piece of engineering, but they are honest about the limitations. Right now, scaling this whole process is constrained by computational costs and, interestingly, by proprietary model API quotas for generating the high-quality data.
Right. They need other powerful models to bootstrap their own data pipeline.
Which leads directly to the provocative thought they leave us with, developing a closed-loop data flywheel.
A closed-loop system, where the new, smarter model is used to accelerate the data generation for the next version of itself.
Precisely. The idea is the enhanced model starts generating its own high-quality QA pairs, its own thinking trajectories, and you use that to scale the data pipeline cost-effectively. It's a self-improving loop. They also note that even though AEPO helps, the core challenge of granular credit assignment inside a long, complex thought process is still an open and very rich area for future RL research.
So the next great frontier isn't just making the model reason better. It's getting the model to generate its own complex training data to fuel the next iteration, closing that loop between capability and data generation. A fascinating challenge to end on.